Welcome to a lesson with Dr. Powell. Let's talk about how we can diagonalize this matrix by using ranges. Let's call this matrix A. We find its characteristic polynomial, x plus 1, x minus 1, minus 1, 2, or negative 2, 0, 0. So what have we done? We've changed all the signs of these guys and just put x's down the diagonal. Check. It looks good. Okay. So then we find the determinant of this to get the characteristic polynomial using a cofactor expansion, this times the determinant of this part. So x plus 1 times, then apply that. So x squared minus x and then minus 2. That can factor. So we get x plus 1, x minus 2. It looks like this. Now, if this matrix right here were diagonalizable, which it is, so I'm just going to tell you that as a given. Now, if it's diagonalizable, the minimal polynomial cannot have any repeated factors in it. This is the characteristic polynomial. The minimal polynomial is the smallest polynomial that will give 0 when you plug the matrix into it. If there's any repeated factors in the minimal polynomial, then the matrix will not be diagonalizable. In this case, you can check by putting the matrix into this, thinking of this as 1 times the identity matrix, and this is negative 2 times the identity matrix. So you get a matrix, x representing this, and x representing the matrix again. So the matrix plus 1 is down the diagonal, times the matrix minus 2 is down the diagonal. That should give you the 0 matrix. And if it does, it's a minimal polynomial and it checks out. We're going to take that granted here, and we're going to proceed. We're going to get 2 eigenvalues, x equals 2 and x equals negative 1. Okay, so, and what we're going to do with those, so let's say, okay, so x equals negative 1 and x equals 2. How are we going to find the eigenvectors for x equals, this is a negative 1, so excuse me, x equals negative 1. How are we going to find the eigenvectors for each eigenvalue? Use ranges. If this is the minimal polynomial, then the range of this part right here, x plus 1 will send to 0. So like the column space, or the output of the columns here, this guy will send to 0. And whatever this sends to 0 is an eigenvector for the value of negative 1. So we just look at the columns of x minus 2 here. So we take our matrix and we just subtract 2's down the diagonal. So we have minus 3, minus 2, minus 1. We have 0, 0. We have, so negative 2, 1, and we have negative 4, 2. Now notice that, let's see. Yeah, okay, I think that's good here. Now, since this matrix, you see the different columns here, which this actually tells us the eigenspace for x equals negative 1 is going to have 2 eigenvectors that'll span it, so a basis of 2, because you have to have a basis of at least 1 for both of these, and you already see columns that are not linearly dependent, so you have some linear independence here. So you may as well just pick the first 2 and just expect that the last guy is going to be in the span of these, which, yeah, if you take, I guess I have to think for a minute. If we took, we can experiment. If we took the negative of this column right here, that would be 2, 2, and negative 1. And then, which looks just like this, except you could add a multiple of negative 3 over and add it to the 2 to make a negative 4. So yes, it is in the span, so that's correct. So we can just pick these 2 guys as our eigenvectors for x equals negative 1. So we can build a matrix, call it U, and I'll just throw those in. Negative 3, 0, 0, negative 2, negative 2, 1. And those correspond to the eigenvalue negative 1. So I will build a diagonal matrix here based upon that. -1, -1. And then 2, I should get one eigenvector for that guy when I look at x minus 2. Let's see what that looks like. When I say -2 down the diagonal, let's say, oh, okay, remember for this eigenvalue, we're going to look at the range of the other guy. Sorry, the range of x plus 1. Okay, so we look at this and we add ones down the diagonal. So we should get 0, 1, 2. And then we have 2, -4, -2. And then we have a 1, 0, 0. And we added 2. We added 1 down the diagonal. Okay, and it looks right. Now, looking at this, I only see one non-zero linear independent vector because these are multiples. These columns are multiples of each other. I just pick that one. So then I have it -2, 1, 1, and I'm successfully, I've made my matrix U and a matrix D so that U inverse A U is equal to D. This technique was by using ranges, focusing on the minimal polynomial, just taking the other part after I've factored it. Thanks for watching.